Hello, my name is Alexander Köbler and I would like to present our work, LVLM-Aided Alignment of Task-Specific Vision Models, published at CVPR 2026. Imagine we want to classify skin lesions with the help of AI. In such a high-stakes setting, a correct prediction alone is not enough. We also need the model to rely on visual evidence that is actually medically meaningful. However, a skin lesion classifier may appear accurate during evaluation while relying on spurious features instead of the lesion itself. For example, it may learn correlations with a colored bandage or another imaging artifact. These cues may be present in the training data, but they can disappear or change once deployed. This can make the model brittle in practice. So the question is, how can we efficiently identify and correct reliance on spurious visual evidence? In such high-stakes domains, task-specific vision models remain important. They are computationally efficient, specialized for clearly defined tasks, and can be inspected with established explanation methods. This makes them practical to deploy and also gives us a way to detect and eventually correct previously explained problematic behavior. For this correction step, domain experts can usually provide knowledge at class level. For example, they can describe what a healthy knee joint should look like, but shortcut behavior appears at the level of individual images. In one radiograph, the model attribution may highlight relevant anatomical structures. In another image, it may highlight an irrelevant artifact. This creates a central gap. Expert knowledge is often available at the class level, but correction signals are needed at image level. Thus, experts would need to inspect many individual explanations and provide fine-grained feedback. This is expensive and unrealistic, especially when experts are medical professionals with limited time. So what we need is an efficient way to turn class-level expert knowledge into image-level correction signals. Our method, LVLM-Aided Visual Alignment, bridges this gap. We combine three components. First, explanations from the task-specific vision model. Second, class-level descriptions from human experts. And third, a LVLM critique and judge. The LVLM acts as a translator. It interprets the model's explanations in natural language and compares it against the human specifications. The output is an image-level alignment signal that tells us which region should not influence the model. In this way, class-level knowledge can be converted into image-level correction signals. Before the LVLM can judge whether a region is relevant, we need to present it with meaningful candidate regions. For this, we introduce PEPS-VGM, or Positive Predictive Effect Probabilistic Segmentation, via weighted Gaussian mixtures. Unlike standard segmentation methods, which are usually based on visual object boundaries, PEPS-VGM is model-centric. It starts from positive feature attributions and clusters spatial image coordinates weighted by how much they positively contribute to the model's predictions. The resulted segments therefore represent regions of positive predictive evidence. This gives the LVLM a structured view of what the model is relying on. The LVLM critique receives the original image, the model-centric segmentation, and the human class description. It then assesses which segments correspond to relevant class evidence and which segments are likely irrelevant or even spurious. For example, in knee radiographs, this may be a hospital tag, and in skin lesion images, it may be a colored bandage. The judge converts the critique's freeform assessment into a structured binary verdict for each segment. These verdicts are then transformed into a correction mask. The correction mask is used to fine-tune the model with a right for the right reason loss proposed by Ross et al. The first term keeps the model optimized for the correct classification label. The second term penalizes gradients in regions marked as irrelevant. This discourages the model from relying on these regions. The important point is that the correction mask was not manually drawn by an expert. It was generated automatically from class-level human knowledge, the model explanation, and the LVLM assessment. We evaluate LVLM-VA on two real-world medical datasets, knee radiographs and skin lesion images. The key metric is worst group accuracy because shortcut learning often harms specific subgroups. Across both datasets, LVLM-VA improves worst group accuracy while maintaining average accuracy. This means the model becomes more robust to spurious correlations without sacrificing overall performance. Compared to group balancing methods, our approach does not require group labels and also provides a human interpretable alignment process. To summarize, LVLM-VA is designed to reduce the manual effort of debugging task-specific vision models. The motivation is that these models are still important. They are efficient and more explainable. But when explanations reveal shortcut behavior, correction often requires costly image-level expert feedback. Our key contribution is to use an LVLM as a bidirectional interface between class-level expert knowledge and image-level model behavior. This allows us to reduce the reliance on spurious features without requiring fine-grained expert annotations. For further details, please have a look at our paper and the provided code.